Hey there, Math 1. This is the concluding video to the 6.1, 6.2 series. We're going to be talking about something called maximum speed here. If you're given a position function over a specific time interval, then we can for sure find the max speed. Now the question becomes, how do we do that? So, first things first. Keep in mind that the maximum value of speed might need to be deconstructed a little bit for us so that we can actually use calculus properly. When you think of speed, first of all, just keep in mind that speed equals velocity without direction. So it's the absolute value of velocity. It's sort of like saying, I don't care if you're going 50 miles an hour towards the origin, 50 miles an hour away towards the origin, you're traveling 50 miles an hour as your speed. So what we can do is we can interpret everything through the lens of velocity, but then we have to make sure that if there's any direction, any negatives associated with it, we take those negatives out and take the absolute value of it. Secondly, when you think about max value, you got to think of the process that we did when we did absolute max and absolute mins. The process for that was take the derivative and then you consider the critical numbers as potential max min values. And then you plug into whatever the original function was that we're talking about. So, we're finding the max value of speed, which means we're taking the derivative of speed. We're considering the Crumbers of speed's derivative. So, this can be tricky. Here's why. You're given position. Given the position of the function is, I'm going to rewrite it as 2 times t squared plus 1 to the negative 1 power. Taking the derivative of it would yield negative 2 times t squared plus 1 to the negative 2 power times the derivative of the inside, which is 2t. That's the velocity function right there. Negative 4t times t squared plus 1 to the negative 2 power. And then you have to find the max value of that function, which means you have to take the derivative of that function. I mean, here's, not to screw with our brains too much, I'm just going to say v of t is essentially speed, because we're looking for max speed, right? But I'm gonna do all the derivatives with respect to velocity, and at the very end we're gonna talk about absolute value. So I need now to take the derivative of the velocity function to consider critical numbers that make the speed or the velocity a maximum value. This is where students always get confused because they're like, you told me to take the derivative, and I took the derivative. Why are you doing it again? Because we're not maximizing the position. We're not saying what's the maximum distance that the position is from the original point. We're saying what's the maximum velocity. So now we got to take derivatives a little bit beyond that. We got to first times the derivative of the second. So I'm using product rule and chain rule intertwined, plus the second times the derivative of the first. So the critical numbers, well, you know what I can do? I can take out a t squared plus 1 to the negative 3 power, and I can also factor out a negative 4. So that gets rid of our negative 4. Our negative 4 takes away this entire t squared plus 1 to the negative 3, takes away this and leaves it with 1, and then you've got negative 4t squared plus t squared plus 1. Which comes out to be our derivative of velocity is -4 times -3t squared plus 1, all divided by that to the third power. So finding absolute max speed means I'm getting critical numbers where this equals 0. So that -4 basically cancels itself out. The bottom is not going to give you any candidates for maximum speed. So you're just left with this right here. T is going to equal plus or minus root 3 over 3. If you solve this equation, that's what you get. Disregard the negative because we're not talking about negative time values. So here we go. Here's our main max candidate, root 3 over 3. Okay, so what we do is we say, consider these values to maximize speed. So we got to put speed in the second column. You take a time value, okay? In this case, it's root 3 over 3. And you ask yourself, what speed does that yield? So what we do is we say, plug this into the absolute value of the velocity function. It's this one over here. The absolute value of velocity is the speed. So I'm plugging into this right here now to check what the actual speed values would be. So over here it's going to be -4t over, instead of the negative exponent, t squared plus 1 squared. So this is root 3 over 3. That's root 3 over 3. I think the easiest way of computing this is to actually assign the variable in my calculator. So I don't know if you guys have ever done this before, but what you can do is you can say, let root 3 divided by 3, you can store that, okay, as a variable. So I'm just going to store it as x. And now what I can do to avoid maybe some of the clunkiness is I can say, we're going to take the absolute value, so math abs of -4x. It's going to plug in root 3 over 3 for me, divided by x squared plus 1, the entire quantity squared. So this is what I'm doing. I assigned root 3 over 3 to x, and then I'm plugging it into the speed function that I've got. This equals 1.299. And I'm assuming that's like what? Meters per second? So at our critical value, it's going 1.299 meters per second. That's not the only point we should test. We should test the endpoints. Remember, the endpoints were also potential candidates for absolute extreme values. So if I plugged in 0, that's going to be an easy one. It's going to be 0 meters per second because it was at rest when it started. Plus, if I plug it in here, the top's going to be 0. 0 divided by any non-zero number is 0, right? And then if I plugged in 5, here's what I can do. I can say, let 5 be stored now as my x variable, okay? And then I just go back up and I hit equals. Oh my goodness, this is nice, huh? So then 0.030 would be my speed at 5. So which one's the biggest one? Here. Find the maximum speed. The maximum speed occurs at t equals root 3 over 3 seconds, but the actual maximum speed itself is 1.299 meters per second. Okay. So that's a tricky one. I'm going to skip over number 6 just for time purposes. All right. This last one will be an interesting one. So we're dealing with the graphs at the bottom. So I'm gonna try something tricky here. It might crash and burn badly, but I'm going to try to move this up. So that we can answer the questions one at a time. All right. Hopefully this doesn't backfire on me. So we're given graphs. This is the graph of a position function. This is the graph of a completely different position function. This is the graph of a velocity function. None of these are related to one another, so don't get the wrong idea about it. So number 7 says, let D and E, I just said that. So these are position functions. Determine if the particle in graph D is speeding up or slowing down. Then determine if the particle in graph E is speeding up or slowing down. So I talked about speeding up and slowing down as if the velocity and the acceleration are both positive, or if they're both negative, this would be speeding up. This would also be speeding up. If they're opposites, that means they're slowing down. So if it's V is greater than 0, but A is less than 0, or V is less than 0 and A is greater than 0, this is when the direction of both the velocity and acceleration are going against each other, and it's slowing the process down. So this is slow down. This is slow down. So how in the world are we supposed to figure this out given the position function? Well, we did a lot of things with graphs of functions that should be super helpful for us. Here's what I mean. Think of V for part D. Think of the velocity as the slopes of the tangent lines. What can you say about the slopes of the tangent lines? They're positive. So if the slopes of the tangent lines to the position function are positive, that means that the derivative or the velocity, whatever you want to call it, is always greater than 0. Now, how can we talk about the second derivative? Well, if you recall, the second derivative was related totally to concavity. When you're given the original position function, 2 derivatives later are all informed by whether or not it's concave up or concave down. So this is, in its entirety, concave up. So the acceleration is also greater than 0. If both velocity and acceleration are greater than 0, it's speeding up. So then when you get a position function like E, the slopes of the tangent lines, well, they're all positive because it's an increasing function forever. So the velocity's positive. The acceleration, it is concave down. So the acceleration would be less than 0. This graph is slowing down. Okay. So I believe that answers the question for part A. The graph for D is speeding up. The graph for E is slowing down. Let's check out the second task. All right. On graph E, so I'm looking at the one at the bottom here, is the particle moving to the left or to the right? Explain your answer. Well, on graph E, my velocity determines the direction that the particle is moving. So the velocity always determines the direction that the particle is moving. So this one would be moving to the right because it's greater than 0. And you know what? All you would have to do for your reasoning is say this. And this is kind of like an AP test question too, where they'll always ask you to explain, but the best explanations are generally just a simple mathematical statement like that. It's right because the velocity is greater than 0 everywhere, from negative infinity to infinity. Or in this case, at least from 0 to 7. That's it for B. For our last one, if I can get this to move properly. All right, I think that'll do it. Graph F represents the velocity function, and it's asking us whether or not it's speeding up or slowing down. So same question that we had on part A, it's just you're not given position. Well, this is all they want you to do. They want you to say the velocity, where we see it, is always above the x-axis. This is the velocity function, so all the y values on this curve are informing us about the velocity. Greater than 0, greater than 0, greater than 0. The velocity is always greater than 0. Now, what would the acceleration be? Well, the acceleration would be the derivative of the velocity. The slopes of the tangent line to the velocity would inform our acceleration. So slope is down, negative, 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 negative. Our acceleration's always negative. So because there's a conflict between the direction that the object's moving, the velocity, and the sign of the acceleration, because they're going against each other, it's slowing down. And again, if this were, say, an AP test-free response type situation, that's your reasoning. It slows down because the velocity is greater than 0 at the same time that the acceleration is less than 0. Okay, guys. I think hopefully this filled in some gaps that maybe were there before the video was given to you. Please email me if you have any questions. Thanks for enduring this semester. It's been a trying one. Adios.